Hi, in this video I'm going to talk about if a function satisfies the Lipschitz condition on the interval negative pi to pi, then the Fourier series converges to f uniformly. Well, to prove this, it suffices to make everything independent of x inside the interval negative pi to pi. Indeed, by the Lipschitz condition, for all x inside the interval negative pi to pi, we have the absolute value of fx plus z minus fx is smaller than or equal to L times the absolute value of z for all z which the absolute value of z is smaller than delta 1. And we see that the previous statement is indeed independent of x. Also, we know that the absolute value of z over sine z over 2 is more than 4 for all z which satisfy absolute value of z smaller than delta 2 is also independent of x. So we know that I1 will tend to 0. This thing is independent of x. So it is left to show that I2 will tend to 0 uniformly. Either for all epsilon greater than 0, there exists an n0 such that the absolute value of I2 will be smaller than epsilon as n greater than or equal to n0 for all x which lies inside the interval negative pi to pi. And here we know that if I2 tends to 0 uniformly, the n0 is independent of x. So to prove this, it suffices to prove this lemma. This lemma states that if fxy is a periodic function in y and f is a continuous function in the square centered at the origin and the length of the square is 2 pi, and for any fixed x, we know that 1 over 2 pi times the integral from negative pi to pi of fxy e to theiny dy will tend to 0 uniformly in x as n tends to infinity. So to prove this, let's call Cnx equal to the expression in the previous page. So let's use the substitution z plus pi over n equal to y. So we get that Cnx is equal to 1 over 2 pi times the integral from negative pi minus pi over n up to pi minus pi over n of fx z plus pi over n e to the negative in z plus pi over n. And notice that this interval here has a length 2 pi, and in this function here is a periodic function with respect to z. And therefore, we know that this interval here can be replaced by the interval from negative pi up to pi. And also we will prove that this expression here is equal to negative of e to the inz. And indeed, if we expand the expression here, we know that it is equal to cosine nz plus pi minus I sine nz plus pi. And we know that cosine nz plus pi is equal to negative cosine nz, and sine nz plus pi is equal to negative of sine nz. And therefore, we know that it is equal to negative of cosine nz minus I nz. And therefore, it is equal to the negative of e to the inz. And we can replace our z by y because z is the dummy variable only. So if we add this expression to the original expression of Cn, we know that 2 times Cn is equal to 1 over 2 pi times negative of the integral from negative pi to pi of fx y plus pi over n e to the iny dy plus the original expression for Cn. And therefore, we know that Cn is equal to 1 over 4 pi times such expression. And from this expression, we know that if n here is sufficiently large, then these two things here will be very close to each other, and therefore Cn will tend to 0 independent of x. So we use this idea here. And we know that if a function is continuous on the square, then it is uniformly continuous on this square, because the square here is a compact set. So that means for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of fxy minus fx prime y prime is smaller than epsilon if the absolute value of x minus x prime is smaller than delta, and y minus y prime absolute value is smaller than delta. So we choose n naught such that pi over n naught is smaller than delta. So we use the identity that e to the I and y absolute value is equal to 1. We know that the absolute value of Cn is more than or equal to 1 over 4 pi times the integral from negative pi to pi of the absolute value of fxy minus fxy plus pi over n. And as y is very close to each other and x is indeed very close to each other, we know that this thing will be smaller than or equal to epsilon by the uniform continuity of f. And therefore it is smaller than or equal to 1 over 4 pi times the integral from negative pi to pi of epsilon, which is equal to epsilon over 2, and this is smaller than epsilon whenever n is greater than or equal to n naught. And here we know that it is independent of x, because in this expression you know that x is already close to each other, because this is x and this is also x, and they are the same value here, and therefore the n naught is independent of x. And we are done with the proof of our previous theorem, because this lemma is equivalent to saying that I2 will tend to 0 uniformly in the interval negative pi to pi. And this is the end of the video about Lipschitz condition implying the uniform convergence of the Fourier series of f. And I will see you in the next video.